Okay, welcome to the first example in the chapter of torsion. The question reads, the solid aluminum shaft has a diameter of 50 millimeters and allowable shear stress of 6 megapascals. Determine the largest torque T1 that can be applied to the shaft if it is also subjected to the other torsional loadings. It is required that T1 acts in the direction shown. Also determine the maximum shear stress within regions CD and DE. Okay, so we can start off by putting the diameter of the shaft in givens, right? So the diameter of the shaft in this case is 50 millimeters. And what else are we given? We're given the allowable shear stress for the shaft. And basically, this is the working conditions. Remember, maximum, the difference between tau maximum and tau allowable and all these different things is basically this is the normal the conditions, the working conditions of the normal stress that this lovely shaft will encounter, right? So T allowable in this case is 6 megapascals, right? And that's pretty much what we're given for givens. We can write down some new formulas because I think, or this is the first time we're talking about torsion. So the shear stress due to torsional loads is equal to the torque, right? The torque acting at the place where you want to find the shear stress, and we'll talk about that in just a second, multiplied by the distance, the radial distance, divided by the polar moment of inertia, right? We did a whole video lesson thing about the polar moment of inertia, so if you need a refresher on that, go to that. But long story short, the polar moment of inertia for a circular solid shaft, I guess, or rod is pi over 2 r to the 4th, right? Okay, that's done. The torque, as we said, we'll explain in just a second. What's C? Well, C is basically, as I said, the radius in this case. If this is our solid shaft, the radius is our C. But it's not exactly the radius. Why we don't put R is, let's say, for example, we had a shaft that looks like this. Well, your C is still, and this is like it's full right here, right? Your C is still your distance to your outer diameter, right? Your outer, there's a correct word for it, but it's not coming to mind. But basically, it's this distance right here, right? So it's from your center axis, right, of your shaft, all the way to the end, the outside diameter, right? The complete outside diameter. Okay, so that's why we put C as opposed to R. But for most, in this case, it's just R. So we'll say that in this case, it's just R. Okay, how about the torque? Well, the torque is a bit different. Like it's the exact same thing we've been doing for beams and stuff for I don't know how long now, and we're gonna get back to it in bending. But it's just the same concept carried on to circular regions now, basically, or torques. So let's say, for example, and we'll do this in just a second, but let's say I want to find the shear stress at this section AB. So I want to find the shear stress in AB, right? How do I do that? Well, if I look at this section like that, and B's over there, and this is A, right? And then I have this 68 Newton meter torque acting right here. I have to put some internal reaction forces, right? I have to have like some, remember when we used to split a beam, right? We had this beam, and then when we cut it, we have to add an M, a moment, a normal force, and a shear force as our internal reaction forces, right? Do you remember that? Hopefully you do, right? We're doing the exact same thing because this thing alone, it cannot, it's static, right? It's not moving, right? So we have to balance it out somehow. And how we're going to do that? Well, we have a reactionary torque acting right here. And the torque in this formula, tau is equal to TC over J. The torque in this formula is this reactionary torque. It's the torque at the specific point where you're trying to find the shear stress. But, and in this case, simply because you only have one other torque at A, so if you want to take the sum of torques from A to B, it's going to be counterclockwise is positive, 68 Newton meters, minus, if you call this T, for example, minus T is equal to 0, right? Because everything's static, right? And in this case, T is just equal to 68. But that's the idea behind it. And hopefully this made sense, but we'll go through it one more time. But it's the exact same thing we've been doing before. You're literally just cutting it open and looking at the reactionary forces, right? But Yeah, and this is positive. Hopefully that made sense. We'll get into the actual fun now. Okay, so that's that formula explained. Hopefully that was helpful. We'll move on to unknowns. And for this entire question, if you understood that part, you're good. That's the entire, I think, the entire chapter of torsion. It doesn't get much harder than that for the entire chapter, unless when we get to the angle stuff. But even that's basically like what we did before with, not deflection, deformations, this axial stuff. But anyway, getting ahead of myself. Unknowns. T1, T max, CD. We want to find, or tau max CD, right? We want to find this force, T1. We want to find the maximum shear stress in this section CD, and the maximum shear stress in this section DE. CD, tau max, DE. Beautiful. We'll start with finding the torque at or this unknown torque, and how we're going to do it is we're going to split the beam right here, and we're going to look at the shear stress. The shear stress of this part of the shaft between B and C, right? We're going to look at the shear stress between B and C, and for this value right here, the shear stress, we know it, right? It's just the allowable shear stress, which is given in the question as 6 megapascals. It's the shear stress that this beam will encounter, right? So that's that. We know C, right? C is literally just 25 millimeters. It's the distance to the outside diameter. And since the diameter is 50 millimeters, it's just the radius, right? And the radius is 25. J is the polar moment of inertia, pi over 2, r to the fourth. We know that. What's torque? What's T? Well, T is the reactionary torque at this specific point where I'm cutting it, right? So if I draw a diagram of this, and actually let's do it over here because this is what the question is asking for. So 3 is, we're going to find T1 using tau CD or BC. Looking at the shear stress between sections BC, right? And if I quickly draw this, like so, it's kind of going to look like that, right? And then I cut it. This is your point C, and refer to this diagram. Your point C is over here, maybe past my cut, right? Because I'm just looking at this section in between, right? Because this entire section is going to have the same shear stress, right? It's going to undergo the same shear stress. This is an assumption we make, and this is reality, right? This is point A. Let's say point B is around here, right? Our torques are, we have a 68 Newton meter torque right here, 68 Newton meters. We have T1 acting in this direction shown, clockwise. And you're going to say, oh, we have at point C, we have 49 Newton meters. Well, no, point C is over here. We're not considering it. We're just looking at anywhere. We can cut the beam anywhere between B and C, right? To end up with this formula. To end up with the formula tau max, or tau, the shear stress between points BC, is equal to the torque that acts at my cut, right? The torque that is acting at my cut, or at my section, multiplied by C, divided by J, the polar moment of inertia. We said C is, in this case, 25 millimeters. J is pi over 2, 25 mm to the fourth. Tau is 6 megapascals. It's the allowable shear stress of the shaft, right? And that is given in the question. And J is the torque that's acting at my cut, right? So let's assume that the torque acting at my cut, we'll call it torque BC, for example. We'll call it torque BC. Torque BC, let's say, for example, it acts positive, right? It acts in the clockwise direction. So torque BC. To balance this out, right? These are the torques that, like the summation of these three torques, will keep the beam stationary. Will keep the beam static, right? Nothing's moving, okay? So easily enough, we just take the sum of torques of BC. of this section, or at our, that's kind of confusing, but basically we're taking the sum of torques of this section, same thing like sum of forces or whatnot. Counterclockwise positive, it's equal to 0. What torques do I have? Well, I have 68 Newton meters minus T1 plus TBC, right? This expression is equal to 0. I can express TBC, which is in my formula, as an expression of these two, right? So if I do that, TBC, the torque that acts at my cut, is equal to T1 minus 68 Newton meters. And just like that, I can sub this lovely guy into my shear stress formula. Everything else is known. I can solve for T1. Beautiful, isn't it? Absolutely amazing. And it takes, like, I think a little bit of effort to get it in the first place, like, to understand. But when you got it, it's easy. All of the questions are this exact same concept. Even the angle questions, which we get to in a bit, they're the exact same thing. So this chapter, absolutely amazing, right? Okay, so we're going to plug all our numbers in. 6 megapascals is equal to T1, 68 Newton meters, multiplied by 25 millimeters, divided by pi over 2, 25 millimeters to the power of 4. Beautiful. So all you're going to do now is isolate for T1. But the most important question is, and for the for the analytical of you, you're going to realize something. You're going to get a wrong answer if you plug the numbers as is. Look at your units. Right here you have Newton meters. You have megapascals here, which is newtons per millimeter squared. Right? You have millimeters, you have millimeters. You have to convert this Newton meters to Newton millimeters, right? Or you're going to get an incorrect answer, right? So please do not forget that, okay? So just divide this by, or multiply it by 1,000, right? I think you multiply 68 by 1,000 to get Newton millimeters. Just do that in my head. I don't know. I think you multiply it by 1,000. But anyway, once you fix this issue, you're going to end up getting an answer of T1 is equal to lovely 215.26. And I'll convert back to Newton meters, right? Because that's how the question expresses torques, right? 26 Newton meters. So that's how you find T1, okay? Beautiful stuff. It also wants us to find the shear stress that acts at section CD and section DE, and basically it's the exact same thing. What we're going to do, we're going to cut it at section CD, take some of torques, use this equation, find our answer this time, right? And then the exact same thing here. So hopefully, if you understood this, it's smooth sailing from here. Make this a bit smaller. Okay, we're going to draw this a billion times again. Okay, so we're going to look at section 4, section AD, right? So if my beam kind of looks like so, or I keep saying beam, my rod, my shaft, looks like so, right? This is my point D. It's somewhere here because I'm looking at the section D. This is my that's a bit too close. This is point C. This is point B. This is point A. 68 Newton meters. T1, right? 49 Newton meters, right? And then at my section, I have a torque. I have a reactionary torque. I'm going to assume it's positive, right? Counterclockwise. And I'll call this TCD, right? I know that this section is in equilibrium. It's not moving. So I can take sum of torques and set it equal to 0, right? So I can see the sum of torques in section CD and positive. And this is an effort to find the torque CD, right? I want to find the torque that acts at my section, right? My cutting section. Set this equal to 0. Take the summation, 68 Newton meters minus T1 plus 49. And I know T1 now, right? So I can plug it in, but I'll keep it like this. Plus 49 Newton meters plus TCD. I understand that TCD is equal from this expression to T1 minus 117 Newton meters. If you plug in T1, you're going to end up getting that TCD, your torque that acts at this specific section of my cut, is equal to 98.26 Newton meters. And all I have to do is plug this into my shear stress formula. The shear stress at CD is equal to my torque at CD, right, multiplied by my distance to the diameter, distance from my axis to the outer diameter, divided by my polar moment of inertia. And that is simply tau CD is equal to 98.26 Newton meters multiplied by, remember to convert the units, 25 millimeters divided by pi over 2, 25 millimeters to the fourth. When you're going to end up getting is your tau CD, your maximum shear stress at this section CD of your shaft is equal to 4 megapascals, right? Just don't forget to convert the units, please and thank you. Okay, the exact same thing now for section DE. 5 section DE or AE, right? So it's going to be messy if I copy it. I'm going to copy it. Just erase this, right? Now I'm also including point D, right? This is my point E. Point D, I forgot what torque acts there. 35 Newton meters. And oh my god, is it positive or negative? It is positive, so counterclockwise. So 35 Newton meters. And I also have my reactionary torque, T DE. Right, so I'm just making a cut in this section, right? Doesn't make sense in my diagram. Just making any cut within this section to find the shear stress within the section, because it will be the same. Because I don't have any, and why it's the same, it's because I don't have any external torques, right, acting within this place, right? Okay. So we run through the same jazz. Plus is counterclockwise. Sum of torques for section DE is equal to 0. I have 68 Newton meters minus T1 plus 49 Newton meters plus 35 Newton meters plus TDE, my torque that acts at my section. I'm going to get that my torque that acts at my section DE is equal to, from this calculation, and including, or I'll write T1 since I did, T1 is equal, or it's equal to T1 minus 152 Newton meters. And what you get from this is TDE is equal to 63.26 Newton meters. Beautiful stuff. Plug this into my shear stress formula. Tau DE is equal to the torque that acts at my section, multiplied by C divided by J. And from this, tau DE is equal to 63.26 Newton meters, 25 millimeters, divided by pi over 2, 25 millimeters to the fourth power. And from this, tau DE is equal to 2.577 megapascal. So this is the torque or the shear stress that acts within your section DE, or the maximum shear stress that will act within your section DE, the maximum shear stress within your section CD, and the torque T1. So those are your answers to this question.